All right, so we are going to start looking at the diffusion equation this week. Sorry about that. I had to find my markers and silence my phone. Okay, so the diffusion equation, we're going to imagine an infinitely long rod, an infinitely long one-dimensional rod. So when I say a one-dimensional rod, what I mean is that it could actually have some thickness. I don't mean a literal one-dimension rod. I just mean laterally it's homogeneous. So we're going to have an equation called the diffusion equation, and this is going to model the spread of some diffusive quantity of substance. So for example, it could be smoke, it could be dye in water, it could be thermal energy density, that sort of thing. But we're assuming that the cross sections are constant, meaning there's not any flow in the up and down direction, or this direction or that direction. There's only flow in along this direction here, from minus infinity to positive infinity. So to set the variables, we're going to have a rho of xt. This is the density of some substance. It's the density of some substance. So it could be like smoke density. It could be the liters of dye per liter, or pounds of dye per liter. If you're looking at dye or pounds of dye per ounce, or whatever the appropriate units are. If you're looking at dye in a pipe filled with water, it could be thermal energy per distance. It could be any number of things like that. What the units are is going to depend on the problem domain. That is the thing that's being modeled. This is a very it's an equation with a very broad application. Okay, any quantity that diffuses can be modeled by this. Okay, so it's the density of some substance. So meaning the quantity of substance from the point x1 to the point x2 is given by the following. I'm going to call it q of t with a semicolon. x1, x2 is going to be the integral from x1 to x2 rho of xt dx. Okay, so rho depends on both x and t. It depends on the fact that it depends on t means that it can change with time. So here x is like the space variable and t is the time variable. So rho of xt is the density of some substance, and I will just add this to say at location x and time t. So it's at location x and time t. This is like the infinitesimal density of some substance, meaning the quantity of substance between points x1 and x2 at time t is going to be this integral right there. Okay, and what we want to do is we want to find a partial differential equation that models rho. So let's set up a diagram here. So this is like the pipe. It goes off infinitely that way, and let's look over this interval x1, x2. Here x1 and x2 are arbitrary. So the change, this change of substance in the interval x1 to x2 per unit time is going to just be the derivative of this q function. So it's going to be the derivative with respect to t times the integral from x1 to x2 rho of xt dx. Okay, this integral right here, rho is a density, right? So the integral is going to be the amount of stuff between x1 and x2. So here, think about stuff as being thermal energy. Think about it as being dye that's that's diluted in water, that sort of thing. And then the change of this per unit time is just going to be the derivative. Well, notice that if we assume that rho is continuous, which that's a reasonable assumption, if we assume rho is continuous, we're integrating over a finite interval here. The integration is with respect to x. The endpoints don't depend on t. I can just simply put the differentiation inside the integral. The only thing that's going to be different, or the only thing that will look a little bit different, is instead of having a regular derivative, it's going to be a partial derivative. So this is going to be the integral from x1 to x2. I'm integrating from x1 to x2 the partial derivative with respect to t of rho of xt dx. Okay, and so I'm going to write over here dq dt is equal to the integral from x1 to x2 times the partial t derivative of rho and then dx. So I'm not going to write the argument. We just need to realize that rho depends on both t and x. Okay. So this is one way to write the change. Here's another way to write the change. So I'm going to introduce a new quantity. Before I can write another way to write the change, I need to introduce a new quantity, and this is going to be called the flux density. So F of xt is the flux density of the substance. So the units, so it is the amount of substance flowing to the right per unit time. So it's the amount of substance flowing to the right per unit time. Now, the reason we call it density, this doesn't really seem like it should be called a density here. The reason we call it a density is because it will be more like a density when we look at the diffusion equation in 2 dimensions. Now we're just doing the diffusion equation in 1 dimension. So it's the flux density, it's the amount of substance flowing to the right per unit time, and I should say this is going to be at location x and at time t. Okay, and even though it's a scalar value, like f of xt is a scalar, it's 7, it's -5, it's whatever it is, I like to draw an arrow over it to make us think of it like a vector. It's very similar to how if you're in 2 dimensions, velocity is definitely a vector, unambiguously, velocity is a vector. However, if you're in 1 dimension, velocity is a number, but it's not wrong to think about it as a vector. Because really when we think about velocity in 1 dimension, we still have speed and direction. The speed is the absolute value, and the direction is whether it's positive or negative. Here, the direction, flux density, it has a direction. It's either going to the right or to the left. And so we can think about flux density as being like the mass flow, or like the absolute value, and then whether it's flowing to the right or to the left. Okay, now of course, since we have negative numbers, it's plus or minus, and so technically it's a scalar value. I just like to write that arrow, that vector arrow, as a reminder that we're really thinking about this as being a flow direction. And so direction is important. It's also important that it's to the right. So a negative value would indicate flow to the left. So a positive value is flow to the right, and negative value is flow to the left. So if I look right here, for example, this would be like f of x2t. And if I look right here, for example, this would be like f of x1t. Now I'm drawing them to the right. If f was negative, it would point to the left. Okay, so now the change of substance, if we're assuming there's no sources or sinks, the change of substance in this interval right here from x1 to x2, the change of substance, the change of substance per unit time in this interval right here is just going to be equal to the rate in minus the rate out. So since we're flowing to the right, the rate in is going to be f of x1t, and the rate out is going to be f of x2t. Now, if the arrow is positive here and positive here, then saying rate in minus rate out makes a lot of sense. It's kind of intuitive that the rate in minus rate out would be f of x1t minus f of x2t. If you have a left pointing arrow here, then think about what happens if it's negative here, what rate in minus rate out means. I guess maybe that's one way to think about it. Okay. So another way to write the change of substance in the interval per unit time is going to be rate in, which is going to be f of x1t, minus rate out, which is going to be f of x2t. Now the rate in minus rate out only makes sense if we're going positive there and positive there. If this is negative, this would also be like rate out. But this is why we want to make sure we have all of our coordinate axes lined up. And if you're unconvinced by my explanation there, I'm definitely leaving some things out. Just think through, there's 4 different cases depending on whether or not the flux is positive or negative there. In 2 dimensions, this actually is a lot easier. You don't have to worry so much about this. Okay, so f of x1t minus f of x2t is also the change of substance per unit time. By the fundamental theorem of calculus, notice that I can write this as the integral from x1 to x2 of minus the x derivative of f x t. And remember, as far as the math is concerned, f is a scalar. I put that vector there just because I want to remind you that the flow direction is important. And in higher dimensions, it is just an absolute vector. Or I don't know, when I said absolute vector, I mean it is unambiguously a vector. Okay, so notice I've got f of x1 minus f of x2. The fundamental theorem of calculus says f of b minus f of a is the integral of f prime of x. Okay, but now I don't have f of a minus f of b. It's more like, I don't have f. So fundamental theorem of calculus, f of b minus f of a is the integral from a to b of f prime, where a is smaller than b. But here I have it in the other direction. I have the smaller one first. So f of x1 minus f of x2 is the integral of minus the derivative, or minus the integral of the derivative. That's what this is. Okay, if I want to maybe do this in one more step, this is equal to minus f of x2 t minus f of x1t. This is minus the integral from x1 to x2 times the x derivative of f. And then I can just move the minus sign on the inside. And this is equal to the integral, I'll step out of the way in just a second, the integral from x1 to x2 of minus the x derivative of f. Okay, but that's also dq dt. That's also dq dt. So I think I'm going to write over here. What this tells us is the following. One way to write dq dt is as the integral from x1 to x2 of the t derivative of rho. That's one way to write the derivative of q. Again, we're fixing x1 and x2. They're fixed but arbitrary. One way to write the change of quantity of substance per unit time in that interval is with this integral here, and another way is with this integral here. So they have to be equal to each other because they both represent the same thing. They're both computing the derivative of q with respect to t. So x1 to x2 minus the x derivative of f dx. And again, rho, the argument to rho is x and t. The argument to f here is x and t. I'm not going to write the variables write the arguments because I'm running out of room here. Now here's what happens. If I add this equation to the other side, what I get is the following. I get that the integral from x1 to x2 of the t derivative of rho plus the x derivative of f is equal to 0. Okay, so now I'm going to erase the middle part of the board here. Okay, and what I've just shown is that the integral from x1 to x2 of the t derivative of rho plus the x derivative of the flux of rho is equal to 0. And notice x1 and x2 are arbitrary. So this is for all x1 and x2, just as long as x1 is less than x2. I mean, it's also true if x2 is less than x1, but that's not how I did it. Okay, what does this tell us? Well, think for a minute what this might tell us about this function here. I'm going to write down a fact. Fact, if f is continuous, and the integral of f from x1 to x2 of f is equal to 0 for all x1 and x2, then f is identically equal to 0. So what this says is if we know the integral of f on every interval is 0, then f has to be the 0 function. Okay, so why is that true? Okay, let's think about why that's true. So assume, I'm going to prove this I'm going to give a sort of pictorial proof here by contradiction. So assume there is an x naught with f of x naught greater than 0. Okay, so I want to assume there's some x naught where f of x naught is not equal to 0. That means it's either going to be positive or negative. I'm just going to assume it's positive, and then you can modify the proof or somehow figure out how to handle the situation where we're going to assume that f of x naught is negative. Okay, so assume there's some assume there's some x naught with f of x naught is positive. So it's positive, so there's some gap between it and 0. So let's say this is f of x naught. Now, since f is continuous, there's some little interval around x naught for which f is going to be positive. Like if x naught is equal to 1 over a million, that's very small, but there still has to be some interval around x naught where f is positive. Because think about it this way. If f of x was positive for all x values bigger than x naught, there'd be a jump discontinuity here. It would be whatever non-zero number it is there, let's say 1 over a million, and then the next, obviously that doesn't make sense, but for all values bigger than x naught, if f of x was 0, there'd be a jump discontinuity, jumping from 1 over a million here, or whatever it happens to be, down here to 0. And a similar argument applies over here. So if, this is where continuity is important, if f is continuous and f of x naught is positive, then there's some interval around x naught where f is positive. So let's just call the left hand endpoint x1, the right hand endpoint x2, and now if I integrate f from x1 to x2, well, f is positive on that interval. I'm integrating a positive value over a positive interval, so that has to be greater than 0. When I say a positive interval, I mean an interval of positive length, of non-zero length. Anytime you integrate a positive function, f is all positive. It's never equal to 0 on the interval x1 to x2. And so its integral from x1 to x2 has to be greater than 0, which contradicts the fact that I'm saying it's 0 here. Okay, so I'm going to erase this. You might want to copy it down because I'm about to use it. But what we know is that the t derivative of rho plus the x derivative of f, its integral is equal to 0 on any interval. And if we assume that they're continuous, then we can assume that this integral or that function is equal to 0. Okay. So therefore, this tells us that the t derivative of rho plus the x derivative of f is equal to 0. Sorry, I have to unlock my computer. Okay, sorry. I don't know if it pauses recording when it goes to sleep or not. Okay. So now what we've just shown, this is something called a conservation equation. And it applies to basically anything to which we can apply the conservation of matter, or the conservation of energy, that sort of thing. All this equation says is that there's no way that if there's no sources or sinks, that the, I don't know, this is just a math way of saying something like conservation of matter. Matter is neither created nor destroyed. If I look at a small section, the only way that the change in substance can be affected is if it's through the boundary. It's through flow through the boundaries. And if there's no sources or sinks, that's intuitive. If I have a pipe, okay, and I have food coloring or some sort of dye in this pipe, and I look at this section of pipe right here, the only way the dye can increase or decrease in this section of pipe is if it flows in or out through the boundaries here or there. There's no other way a dye can come in or out of the pipe. That's what this says right here. So, so far, all we've used, we haven't used the fact that we're looking at a diffusive substance, though we are in general, or not in general, specifically for this week, we're going to be looking at diffusive substances. But this is something that's true basically for any substance, as long as the conservation of matter applies to it. Okay, so now, if we know the substance, if we know the substance is diffusive, we can actually write F as a function of rho. And you'll see what I mean in just a minute. So what do we think about when we think about a substance being diffusive? To me, it means that it's going to spread out. In other words, it's going to go from areas of higher concentration to areas of lower concentration. Okay, it's going to go from areas of higher concentration to areas of lower concentration. Right? Like if you imagine putting a drop of dye into water, the dye is going to spread out. It's going to go from higher concentration to lower concentration. It's not usually, for most dyes and most water, I guess there's only one type of water, it's not going to clump together, it's going to spread out. Now, of course, there are some things that do clump together. That would not be modeled by this equation here. We're looking at things that spread out. Okay, so if we know the substance is diffusive, then it follows Fick's law. It follows Fick's law, which says that the flux density is equal to minus some function k of x times the derivative with respect to x of the density here. So k is some positive function that depends on the medium. So k of x would depend on the medium through which this thing is diffusing. Okay, you can imagine some media might be very open to diffusion, and some media might not be open to diffusion. It might not diffuse a lot. Okay, so if we think about this, if the x derivative of rho is positive, that means that we're increasing. So let's look at this point x right here. Okay, if the x derivative of rho is positive, it means the density is increasing. And so we have higher density here and lower density here. And so the flux is going to be from high density to low density. So if the x derivative of rho is positive, that means we've got increasing density. The physical intuition tells us that the flux should be in that direction. In other words, the flux should be negative. So the flux should have the opposite sign of the density, of the derivative of the density. And that's exactly what we have here. Okay. So then the flux density is equal to minus k times the x derivative of rho. Okay, well, what happens if I take my expression for f and just replace it in that equation there? I'm going to get the following. I'm going to get that the t derivative of rho is equal, I'm going to get the t derivative of rho plus the x derivative of f, but f is equal to minus k times the x derivative of rho. And this is equal to 0, or I can say the t derivative of rho is equal to minus, when I add this, well, let me just do it. It's going to be minus the x derivative of minus k times the x derivative of rho. The minus signs cancel, and we get the t derivative of rho is equal to the x derivative of k times the x derivative of rho. Okay. And so now, if rho is the density of some substance, and now we need to say some diffusive substance. If rho is the density of some diffusive substance at location x and at time t, it satisfies the following one-dimensional diffusion equation. The t derivative of rho is equal to the x derivative of k times the x derivative of rho. And if k is a constant, we can pull that out, and it says k times the double x derivative of x of rho. So if k is constant, so the 3 lines here means it's just identically equal to some constant, then we can write this as the t derivative of rho is equal to k times the double x derivative of rho. Okay, but we can only do this if we know that that k is constant. Okay, and so this is the one-dimensional diffusion equation. A lot of times in PDEs we like to use the letter u to denote an unknown function. So a lot of times you'll see this as the t derivative of u is equal to the k times the double x derivative of u. Okay. I get that was a lot. That was a long video, a little longer than I had intended. In the next video, I'm going to show how we can go from the diffusion equation. If rho, for example, represents thermal quantity, I'm going to show you how we can relate that to the temperature of the one-dimensional rod and get the thing that's called the heat equation.